So we're going to talk through the small-scale pit procedure because while this is conducted typically by, at least in my experience, typically by geotechnical subconsultants, it's important to understand what goes into the test. First of all, we need to dig down to the actual infiltration horizon that we're going to intend to use. And so if we're going to go out and do 8 feet of cut on our site, and then we're going to put our bioretention facilities in at that elevation, that means we need to excavate down 8 feet, and then we need to cut another 36 inches to get down to the actual infiltration horizon where our facilities will be in the design. So that's important because if we initially go out and we conduct our pit tests on site before we have our grading plan done, it's possible that we will not have conducted our pit test at the right elevation. So that's why I really advocate for this kind of two-phase approach where we go out, we do our reconnaissance level information, we figure out what's going on, we do our plan. So we get sort of planning level infiltration information, do our conceptual design, and then we go out, and once we've got our grading plan done, we go out and we get our final design values kind of once we know where these facilities are going to go exactly and at what elevation. But essentially we excavate out the side. There's a minimum horizontal bottom area there. You can see it's 12 to 32 square feet, so these are larger. We're laying back our side slopes. We're putting in a vertical measuring rod and put a splash plate in, which is going to reduce the erosive force of the water coming into the cell. We're not going to kick up silty material. These tests take a long time. So they take multiple hours. So we go in and we got to do our pre-soak period. We're going to put the water in 12 inches deep for 6 hours, and we're going to really saturate the soil, and we're going to continue to put water into the cell until we kind of reach a stabilized infiltration rate, which is really we're maintaining that 6 to 12 inches for an hour. And so then what we do, once we've pre-soaked for 6 hours and we run our infiltration rate, we run our water in where now we're maintaining a level in the cell, so we've recorded that rate. We see how much water is coming in. That's the same amount that's kind of infiltrating with a little bit of head in there, and we realize, okay, we're at steady state. We turn off the water, and then we continue. Then at that point, we do a falling head recordings, and we record the level as it drops every 30 to 60 minutes, depending on rates and so forth, to get a nice curve, so that you can establish the slope of that line, which is going to be essentially your design infiltration rate. So it's basically the lowest hourly flow rate is the initial infiltration rate, meaning that as you're recording those values and the curve starts to become linear, and really it's the slope of the curve at the end I'll show you in a second, and that's the rate, that's your initial rate. It's after the pre-soak, after the constant head, it's the falling head part, the lowest rate during that phase, and that's your rate. So then once we've conducted the test, then it's important to continue digging because we want to make sure now that we've just run that test, are we sitting a foot above till? What's going on? And so it's important to then continue digging 3 more feet down and just investigate what is happening below our test and see if we can find our soil modeling and so forth to find evidence of groundwater. Alternately, and this is all worked out with the jurisdiction, monitoring groundwater may be required or necessary to ensure that we've got the right vertical separation that we need. And this is often discussed. We really do want to see the pit test conducted in the winter, really to have it be a wet season test, to be the most representative of the kind of the worst case or the likely design case for the system. Construction schedules don't always tolerate that, and that can be a negotiation with the jurisdiction about appropriateness of whether that timing is going to work and what other information can be presented by the applicant to kind of show that we really do understand what the seasonal high groundwater is. Whether we're going to monitor, we've got good evidence of modeling or what have you. But the recommendation going into that process is to really do this test kind of in the later part of the winter when we expect groundwater to be the highest. So that's an often discussed and negotiated issue, as is the second point here, which is the number of these tests. And the manual has a requirement or a suggestion about the number of pit tests that should be used in a site. But however, this is also an area in my projects that is negotiated based on working with Geotech and with the agency about what the appropriate number of these tests, because they take a day to conduct. They can be $2,000 or $3,000 a test. How many of them we need to have or should have is, again, it's kind of based on site conditions. But going into that discussion, 1 pit test per facility or one pit test per 5,000 square feet. That's essentially for pervious pavement applications. Because typically bioretention cells are a little smaller than 5,000 square feet, but if you did, you could have multiple per cell. And then on long, narrow facilities like roadside bioretention, the recommendation is 1 every 200 feet, but that's a bit aggressive in my view. I've never actually done them that frequently on projects, and so it really becomes a part of your initial soil assessment where you're going and you're doing your Vector borings. And maybe your Vector borings are that frequent, and then based on the consistency of your Vector borings, you can decide how many pit tests are appropriate to adequately represent the project. So the equipment to conduct the test, pretty straightforward. You either need to develop a water source from a hydrant, if that's allowed, or you need to secure a water truck. And wherever your source of water is, some places allow the use of hydrants, other places don't. Water truck, depending on your soil infiltration rate as well, can determine what source. I worked on a project down in Snohomish County where we had very sandy soil, and a water truck actually wasn't going to be enough, so we had to actually stretch a lot of hose. A couple of the pits, we actually set up a portable tank and we were shuttling water, and it can be pretty involved. You have to get yourself a source of water. You need a lot more water if you've got sandy soils. And then you've got your flow meter, and then we go off to the pit. We mentioned the vertical measuring rod. The 5-gallon bucket in this case is acting as our splash plate. What most people do is set up a data logger, have an automatic logger logging the depths. I guess alternately you can have a clipboard and read it physically off of the measuring rod. These tests go on for a long time, and that can be a bit tedious, but either one would work. What you get is something that looks like this as a result. And so the light blue line is the flow rate, the measured flow rate coming through the meter. The dark blue line is the level of the water in the pit. So you can see the light blue line spikes up as we're basically filling up the pit, and then you can see the water level kind of stabilize there right around 1.3 feet, 1.25 feet of ponded depth. You can see the blue line down, the light blue line down below. We dial it back to the point where we're putting the amount of water into the pit to achieve that, essentially that steady state that you see up there. So you can see they dialed back their pit or their meter to achieve. We're going to look at the flow rate on the right. So it's going to be like 0.3 GPM. So 0.3 GPM held the level constant in the pit. They measured that for a period of, you can see there, an hour, and they realized that, yep, there it is. The constant head portion of the test is running at 0.3 GPM. We've reached steady state. Okay, it's time to shut off the water. And they turned off the water and then continued to log the depth as the pit drained down. What you can notice, if you look at the times, this is a very long duration test. This one essentially is lasting over 24 hours. You see that? They started at 9 a.m. on March 8th. And they finished at noon the next day, March 9th. And so this is where having an automatic data logger is going to be probably worth the investment. Point being, you can see that curve as the water level drops in kind of a nonlinear way, and then it kind of reaches a little bit of a linear tail there on the end. And it's really that rate on the far right of the curve there where you can see that essentially the amount of volume over time, or the drop of the water in the pit over a period of time at the end, those last three little data points there on the right, set the measured rate, which is 0.25 inches an hour. So the result of this test is an initial measured infiltration rate of 0.25 inches an hour. So a pretty relatively slow test. And then so once we've got that piece of information, then it's time to apply our correction factors. The first one is the soil variability and number of locations tested factor, which as far as I can tell, there's not hard and fast guidance on that. How many tests is considered variable and so forth, but that's a professional judgment involved in applying that factor. Then there's a correction factor for the test method, for each test method. And then the last one is the degree of influent control to prevent siltation and biobuildup, which is always one when we're working on low-impact development sites. So this same set of correction factors would apply if we were working on a dry well design, and we're using these pit results to design a dry well where we don't have influent control. So the bioretention cell itself is considered fully protective of the subsoil, of the soil we're testing. So because we're doing bioretention, it's necessarily one. If we were not doing low-impact development and we're over here doing a dry well using our large-scale pit, and say we just don't have good, I don't know why we wouldn't, but we just don't, we're just going to let a bunch of untreated water go to our dry well, then we would use something other than one for that. But that's beyond the scope of this discussion. So as far as our bioretention design today is, we're using one every time. And then what we do is we pack them all together. We come up with essentially a blended total correction factor, apply that to our initial rate, and then we come up with our design rate that we plug into our model to understand how big the bioretention cells need to be. Yeah, so we pack this all together and we come up with we come up with our design rate, and that's how we use that to size our facilities. Yeah, so the question is, do personnel need to get in the hole, and how does that affect shoring and other OSHA requirements around safety? I think given the example we're looking at here on the screen, it does seem like we probably could lower that stuff down ourselves, potentially, and we would not need to get in the hole. So I think it's possible, but also we may need to be prepared to have shoring boxes if someone's in there, but we need to pull those shoring boxes out so we can get an accurate test. Similar to what we did 10 years ago for bioretention, is allowed for sizing rain gardens that are not engineered. So that, just to be aware of the difference there.